In this lecture, we are trying to get the matrix representation of angular momentum in the Jm basis. So since J square and Jz commute, the set of their common eigenstates, Jm can be chosen as the basis for this matrix representation. And this basis is discrete, orthonormal, and complete. It's discrete because we have seen that J and M can have only certain values. 0, either half integer or integer values, and its normalization condition for this basis can be given as J prime M prime J M is given by delta J prime J delta M prime M, and the completeness condition means sigma M equal to, M can have values from minus J to plus J Jm. Take the projection operator, the sum of all projection operators Jm must be 1 or I, the identity operator or the unit matrix. So this is what we mean by the completeness condition of this basis. And we have seen in previous class that J square and Jz have common, or they have this Jm basis as their common eigenstates. So they will be diagonal in this basis, because you can write J prime M prime, then for the J square matrix we can write it as Jm is equal to H cross square J into J plus 1, its eigenvalues. Then we have delta J prime J delta M prime M. Similarly, for the matrix elements of Jz, we can write J prime M prime Jz Jm, and its eigenvalue equation is H cross M. Then the orthonormality condition demands us delta J prime J delta M prime M. So these two equations tells us that the matrix of J square will be a diagonal matrix with the magnitudes given by H cross square J into J plus 1, and the matrix for Jz will also be a diagonal matrix, and the values of those diagonal elements are given by H cross M. So these matrices are very easy to observe or to realize in matrix form. Now, since J plus or J minus do not commute with Jz, these matrices for J plus and J minus are represented in the Jm basis by non-diagonal matrices. So we can write it as J prime M prime, then J plus or minus Jm is equal to H cross into, please check the last class, H cross into J into J plus 1 minus M into M plus or minus 1. Then we have delta J prime J delta M prime M plus or minus 1. Similarly, the matrix for Jx and the Jx matrix for Jx can be written as J prime M prime Jx Jm. This is equal to H cross by 2 into square root of J into J plus 1 minus M into M plus 1. Then we have, in this case, we have delta M prime M plus 1 plus, there is another term which is given by square root of J into J plus 1 minus m into m minus 1, then delta m prime m minus 1, then we have delta j prime j. Similarly, the matrix for jy can be written as j prime m prime jy jm is equal to h cross by 2I the square root of j into j plus 1 minus m into m plus 1 delta m prime m plus 1 plus square root of j into j plus 1 minus m into m minus 1 delta m prime m minus 1. I made a mistake. This should not be plus. This is minus. Then delta j prime j. So these are the matrix elements for various operators j square, jz. Those are diagonal matrices, and then we have non-diagonal matrices for j plus or j minus, and also non-diagonal matrices for jx and jy. So now let's consider one particular example. Let's consider the case for the quantum number j is equal to 1. We are going to find out the matrices for this particular case for all these operators. Now for j is equal to 1, we know that the allowed values of m can have values from minus j to plus j. So minus 1, 0, plus 1. So the joint eigenstates of j square and jz are in the jm basis. We have the jm basis. So the all possible eigenstates are 1, minus 1, 1, 0, and 1 plus 1. Okay, so these are the possible eigenstates of j square and jz. Now if you try to get the matrix elements of j square operator, can see that from the previous expression we have seen that it will be a diagonal matrix, and so we will be having only the diagonal terms, and all other terms will be 0. Now what is the magnitude of this diagonal element? It's given by eigenvalues are given by h cross square into j plus 1. So this is for j square, right? So for j square, for this particular example we have taken j is equal to 1. So this will give us 2 h cross square. So we get 2 h cross square as the diagonal values, 2 h cross square. Okay, so this can be written in a compact form. The j square matrix can be written as 2 h cross square into 1 0 0 0 1 0 0 0 1. Okay, so in this representation, actually when you write in the matrix form, you can consider it like this. We take our j and m values along this direction, and j prime m prime values for this direction, along this direction. So for this particular example, the possible values for j is 1, and for m it is 1 0 minus 1, and j prime is also 1, and for this one is 1 0 minus 1. So this is our one state, this is our 1 0 state, and this is our 1 minus 1 state, like that. So that is the way we have written this matrix. Okay. Now what are the elements of J search? Now the J set, again we have a diagonal matrix. So you can see that for J search we will be having only a 3 by 3 matrix, because M can have values +1, 0 and -1. So its eigenvalues are given by MH cross, right? So if you remember the M and M prime values, here we have 1 0 -1, 1 0 -1. So this state, the eigenvalue expression, we have seen that its matrix elements are given by MH cross delta J prime J delta M prime M. So all these non-diagonal elements will be 0. Now what is the magnitude of these diagonal elements? It's given by MH cross. So it depends the value of the quantum number M. So here it is 1 H cross, here it is 0 H cross, and here it is -1 H cross, right? So this can be written as H cross into 1 0 0 0 0 0 0 0 -1. So this is the matrix form of J set. Now for the J minus matrix, we have seen that, so if you consider this expression for J plus and J minus, we can get the matrix elements from this expression. For example, if you are considering J minus, we will be having the eigenvalues or the magnitudes given by this term H cross into all these terms, and the non-zero elements are determined by these parameters, these two delta functions. So we have seen that we have non-zero elements only when J prime is equal to J, and only when M prime is equal to M minus 1. If you are considering J minus operator, or if you are considering J plus operator, you have non-zero values when M prime is equal to M plus 1. Okay. So let's try to get the matrix elements for J minus. So for J minus matrix elements, we have delta J prime J and delta M prime M minus 1. This delta J prime J condition will always be satisfied for all conditions, because we have considered for J is equal to 1 case only. Then we get non-zero terms when our M prime is equal to M minus 1. Okay, so that is, you can write as for 1 0, let's consider a particular state 1 0 J minus 1 1. See, this will be a non-zero element, because you can see that here M prime is here and M is this one. So M prime is M minus 1 in this particular condition. Similarly, you can have non-zero element for the state 1 minus 1 J minus 1 0. You can see that this M prime is this M minus 1. So we have non-zero elements only for these two conditions. Okay. Now the magnitude of these non-zero elements are given by H cross into square root of J into J plus 1 minus M into M minus 1. So you can write that for m is equal to 1, j is anyway already 1, so you can write it as this magnitude will be h cross into square root of 2. So you can write it as it is root 2 h cross. And for m is equal to 0, this is given by root 2 h cross again. Okay, so the matrix element for j minus can be written as the magnitude is given by root 2 h cross in both cases, root 2 h cross. Then if you look into j prime m prime 1 1 0 minus 1 1 1 0 minus 1, we have seen that the non-zero elements will be there for 1 0 and 1 1 states. So we have first non-zero element here, and this its magnitude is given by root 2 h cross, or this will be 0 0 0 0, and again we have non-zero element here, it is given by root 2 h cross 0. Okay, so what you can write, you can write the matrix element for j minus. The matrix element for j minus is given by root 2 h cross into 0 0 0 1 0 0 0 1 0. So this is the matrix element. Now this I have written just for you to understand how to get these elements. So this is the matrix elements for j minus. So once you know the matrix elements for j minus, a similar argument can be given for the matrix elements for j plus, and in this case the condition is delta j prime j delta m prime m plus 1. So this condition is always satisfied for this particular example, and we have non-zero elements whenever our m prime is equal to m plus 1. So what are the various possibilities that we can have for non-zero elements? This is 1 1 j plus 1 0 and 1 0 j plus 1 minus 1. In both these cases you can see that this m prime is m plus 1, here also m prime is m plus 1. So you will get non-zero values for these two elements only. For all other combinations this condition will not be satisfied, so you will get 0 diagonal elements. So you can write for j plus, it is given by square root of 2 into h cross 0 1 0 0 0 1 0 0 0. So this is the diagonal elements for the j plus operator. Now the matrices for jx and jy can be obtained from these two expressions. For example, for the case of jx, you can see that we have two delta conditions, delta m prime m plus 1 and delta m prime m minus 1. So for these, whenever these two conditions are satisfied, we will be having non-zero diagonal elements along with this condition, and for the particular example that we are considering here, this is always satisfied. This condition is always satisfied. The same is the case with the jy matrix. Whenever these two conditions are satisfied, you will get non-zero diagonal elements, and this is always satisfied. So let's see what are the matrix elements for these two matrices jx and jy. So for jx, it is given by square root of 2h cross by 2 0 1 0 1 0 1 0 1 0. So this is h cross by root 2 into 0 1 0 1 0 1 0 1 0. And for jy, this is equal to h cross by 2 0 minus I 0 I 0 minus I 0 I 0. So these are the matrix elements for jx and jy, and these can actually even without getting these values, you can write it from the known values of j plus and j minus, because jx is given by half of j plus and j minus. So if you add these two matrices for j minus and j plus, and then you take half of that, that's what you have seen here. Now for the j minus, this is simply 1 by 2 I of j plus minus j minus. Okay, so this can be written as I by 2 of j minus minus j plus. So from the difference of j plus and j minus, you can get this matrix, or you can use the expressions with the delta functions to get these diagonal elements. Okay.